So now that we're done talking about parallel resonance, and we still need to go back to that because apparently there's more about this parallel resonance because in reality, in practical applications, our inductors are non-ideal. So when we say non-ideal, they are not pure inductive. Our coils are always in series with their resistance. So in real cases, the circuit will be, so if you have a parallel coil, so the coil should be in series with the resistance. That's the coil. The inductor and the coil and the resistance are in series. So this is the coil. This is the non-ideal inductor because this inductor has its own resistance. And if we take that in parallel with a capacitor C. So if this is the case, if we have a voltage V and we have a current here I, and if this is R, L, and C, then what will be the condition for us so that we are in resonance? If we review our conditions in series and parallel resonance, ideal resonance, in the last discussions, they have the same conditions for this resonance. And that condition is when X of L, the inductive reactance, is equal to X of C. And this is only true for ideal cases. Why? Because the real definition of resonance is when the net reactive power of the circuit becomes zero. So when it becomes zero, the power now that is being delivered to the circuit will be just uh, pure real power. So this means if it's a pure real power, it's just real power. There's no other components or reactive power, net power will become equal to zero. Then the circuit means a pure resistive circuit. So if it's a real power, it's only real power, it means it's a pure resistive circuit. And that is also the cases for the previous discussions for the series and the ideal parallel resonance. When XL is equal to XC, the circuit becomes pure resistive. And that is the time when the current becomes maximum or the voltage becomes maximum. And that is the resonance phenomenon. So in this case now, if we apply again this XL equals XC. Now, if you want to, again, take note of the condition, the reactive power, net power should be equal to zero. So if you want to solve for the reactive power at C, you know the voltage here, that will be just equal to V squared over C, XC. While the reactive power on the L, and if XL is equal to XC, the voltage across L now will not be equal or the same voltage as the voltage across the C. So if that is the case, then therefore their Qs, even if XL and XC are the same, will not be equal to, will not be the same also. And they will not cancel out and it will not be equal to zero. So if it's not equal to zero, then it's not the resonance phenomenon. Why? Because the circuit will not be a pure resistive circuit because there's a difference between the Q here and the Q here. JQ of the capacitor, it's negative, and for the inductor, it's positive QC. So if you add that, it should be equal to zero when QC is equal to, this is L, QL, and that's only true if they have the same voltage. But in this case, if they are in series, it's okay. They have the same, even if they don't have the same voltage. If they have the same current, that's fine. But here, we cannot say that they have the same current. In series circuit, it's always the same. It's because they're series. They have the same current. But here, it's not true. We cannot say that. So this condition now will not be valid in this case. So if you have a resistance here, this is not valid for this case because this will not become zero. Okay? They will not become zero because they don't have the same voltage across the inductor and the capacitor. If they have the same, then it's fine. It will always be equal to 0. And what should we do? How do we determine now the condition so that for this circuit to be in pure resistive, so that it will be in resonant phenomenon? So we need to solve for the current. Let's call this current IL, the current flowing through the coil. And we have another current IC, the current in the capacitor. Now, if we try to draw the vector diagram or the Phasor diagram of this current, we have here, if this is the voltage, the IL, or the inductive current, because this is RL, it should be lagging somewhere here. This is our IL. If this is our voltage, it should be lagging by some angle. We can call it VL. While the capacitor, because this is a pure capacitor, we know that a pure capacitor, the current in a pure capacitor is always leading the voltage by exactly 90 degrees. So it's somewhere here. This will be our IC. Then, to make this, remember, we want to make the circuit pure resistive. So when will it be pure resistive? When will it be pure resistive? When this is 0. When is that? When the current, total current, is in phase with the voltage. So what happens if they are in phase? If they are in phase, this means the circuit now is in pure resistive circuit. Is a pure resistive circuit. So that is what we want for a resonance to happen. So we want to make our current to be in phase with this voltage here. But before we do that, IC is just this component here, while IL has two components. We have the component here, the X component, and another component here for the Y component. This X component, this is just equal to, using Sokotawa, you can use Sokotawa here. If you know the angle here, this side here, this is a right triangle. Your hypotenuse is IL, then this should be equal to IL times sine or cosine, because this is a decent side. This is the decent side, so this should be cosine of that angle phi. While this one, this component here, because this is the same as this, it's the opposite of this angle. So IL, this will be IL opposite, so sine of VL. These are the two components of IL. Now, let's try to observe. Again, what do we want? We want the total current to be in phase with the voltage. Now, if we add IL and IC, these two components or two currents, it should be equal to somewhere in this line, in this voltage here, because they are in phase. So, how do we do that? How do we do that? We do that by equating this side with this side. The Y component of IL, we equate that with the actual value for the IC. And if we do that, the only remaining value now will be component is this component here, which is in phase with the voltage. This will be in phase of the voltage. So if we add these two, we cancel these two, the only remaining current will be this current here. And that is what we want. We want that to be in phase with the voltage. So this will be our total current I. So in order for us to do that, we need to make IC equal to IL sine phi. IC should be equal to IL times sine phi. The magnitude of IC should be the same as the magnitude of IL sine phi L. So that if you add these two, that will be equal to 0. Okay? So this is the condition now for us to have a pure resistive. So that the current, total current, will be this one, I here, which is in phase with the voltage V. And it is now in a resonance phenomenon because it's acting like a pure resistive circuit. And IL is equal to, or I is equal to IL sine or cosine of phi, PL. Then remember, this phi here, this is the angle here in RL. So we can call that R the impedance here. to be just equal to ZL, and this is just equal to R plus JXL. So if we plot this impedance with the impedance diagram, so remember the impedance diagram, this is our R, this is our XL, and this is our ZL. And the angle here will be phi L, because this is our ZL, impedance triangle. So from here, we can determine what is sine of phi L. So what will be sine of phi L using SOHCAHTOA? So sine of phi L, what's the opposite side? The opposite side is XL. Then what's the hypotenuse? The hypotenuse is ZL. So that will be our sine of phi L. Then also, if you look at this diagram, the circuit, we know the voltage across here. We know the voltage across here. So if I solve for IL in terms of the voltage, IL will be just equal to, by using Ohm's law, the voltage at that point, that's V, divided by the impedance at this point, and that will be the current. The impedance here is the total impedance of the coil, and that's just ZL. So this is Z times L. While for IC, it's the same. The voltage here is V, but the impedance at this point here will not be equal to ZL because this is C, and it's only the reactance that is in that. So this will be V all over X of C, because we don't have R here, and that is our IC. So we can substitute this now in our equation to solve for IC. So IC will be equal from here, IL times sine phi. Our IL is V over ZL. You multiply that with what? We multiply it with sine phi L. Sine phi L, we already solved that here. That is X of L all over Z of L. And this is equal to, from here, because this is IC is equal to V over XC, this is equal to V all over X of C. Then we can cancel out the voltage. And we have remaining, we can cross multiply. ZL squared now will be equal to XC times XL. XL times XC. And what is ZL? Again, ZL is this one. So if we solve for the magnitude of ZL is just equal to the square root of R squared plus XL squared. And if this is squared, then therefore this is just equal to R squared plus XL squared. We just remove the square root because it's square. Then XL, what's XL? XL is equal to omega times the inductance, or the inductance, while XC is equal to 1 over omega times C, the capacitance. So if you multiply these two, omega will cancel out. So we only have L all over C. So this is just equal to L all over C. And again, we have here X of L. So what is X of L? This is omega L. But omega L is 2 pi FL. And what's the frequency here? The frequency now here that we are solving, this is now our resonant frequency. Why? Because we meet the condition, the circuit is pure resistive, acting like a pure resistive. Why? Because we equate these two. So if these are equal, then therefore it acts like a pure resistive circuit. So if it acts like a pure resistive circuit, then we are in resonance. So now we can substitute that. So R squared plus our XL is just 2 pi times F. This F now will be the resonant frequency multiplied by the inductance L. Square that, and this is equal to L over C. And we take R squared at the other side, so we have, and we take the square root, so we have 2 pi F or L will be equal to L over C minus R squared, and take the square root. Then solving for F of R, then we have F of R equals 1 over 2 pi times L. We can put this L inside the square root here, so that this will become, so this is just L. So if you put it inside the square root, it will become square. So we have now L over C, then I have 1 over L. You put it inside, it will become 1 over L squared. So if you multiply that 1 over L squared with L over C, the L at the numerator will cancel out with the 1 L in the denominator. So we only have 1 remaining L in the denominator, and we cancel out the 1 in the numerator. Then we have still, this is, this should be r squared. This should be r squared. Then you divide it with 1 over, or multiply it with 1 over L squared again. And this will be the formula for the resonant frequency in this case with a non-ideal inductor. So if you look at this, so if we have, look at the equation, if we have an R that is very negligible or small, so if we neglect this R, so it means it's just L and C. So what happens to the formula? It will be equal to 1 over 2 pi times the square root of 1 over LC, or 1 over 2 pi the square root of LC, which is the formula for a normal, ideal, parallel and series resonance. Okay? Now, what happens if we also have a non-ideal capacitor? So we have another resistor here, somewhere in series with the capacitor. So with a non-ideal inductor and a non-ideal capacitor in parallel, so we have an inductor and we have a non-ideal capacitor. So we can derive again our solution, our resonant frequency, the same method as we did here in the first one. So let's call this one R1 and this one R2, and we have L and C. Then we have voltage V and current I. So if we apply again the same method as we did here by drawing the phasor diagram of the current. So let's name the current here. I can just name this RL and this one RC, so that later on I will not misplace them. So if this is IL, the current flowing through the coil, and the current in the capacitor is IC. Now, so if we plot that again in our phasor diagram, so this is our voltage. So again, IL is somewhere here. It's lagging the voltage. So this is the voltage. IL is lagging the voltage by some angle phi L. And this time, our X or IC now will not just be going upward because we have a resistor here. So it will be in this direction. So I will call this IC, and I also call this one phase of C. Okay, phase of C. So if I draw the components again, so that we can imagine this component here. And another component here for IC. So this component here, if this is phi C, it's the opposite, so that's sine. That will be IC times sine of phi C. And it's the same as if you draw a line here, this vector here. This is also that one, IC sine phase of C. Then for this part, this will be IC cosine of sine P over C. And for the inductor, we have here this one. This is the y component of the IL. This is IL, and that's opposite. So IL times sine of phi L, and this will be the x component, and that's IL cosine of phi L. Then I also draw I here. It's the same thing as this current here. This is IL sine of phi L, and this is IC sine of phi C. Now, so look, if we look at our Phasor diagram again, and remember what we want I to be, the total I, the total current to be in phase with the voltage V. So in order for us to make that, we need to equate again this one and this one, so that we just need to add these two current, and that will be the current, and it will be along the x-axis, which is in phase with the voltage V. So we just need to equate these two. So we have now IC sine of phi C is equal to IL sine of phi sub L. And we can derive again for sine phi L from our previous discussion here. Sine phi L is the same. It's XL over ZL. So this will be XL all over ZL. And the same true as sine phi of C. This is also equal to, let's just rename this to C instead of L. So this is just equal to X of C all over Z sub C. And for IC and IL, using Ohm's law again, we know the voltage here, we know the voltage here. So we can solve for IL first. IL will, using Ohm's law, the voltage across this is V. You divide it with the impedance ZL. And for IC, it's the same, V all over, but instead of ZL, this will be Z sub C, because this is the impedance of RC and the capacitor C. Then we can now substitute this here in our equation. So IC is V all over Z sub C times sine of phi C, and is XC all over Z sub C. And this should be equal to IL is V over ZL times sine of phi L, that's XL all over ZL. And we can cancel out V, so we have XC all over Z squared C is equal to XL all over Z squared L. And what is ZC and ZL? ZC is equal to RC. So ZC is equal to the square root of RC squared plus XC squared, while ZL is equal to the square root of RL squared plus XL squared. If we square that, so we have XC all over the square of this, and this RC squared plus X of C squared. And this should be equal to XL all over Z of L squared. So this is just RL squared plus XL squared. And these terms are somewhat familiar, and actually they are familiar from basic circuit. This is actually the susceptance of the circuit. That's B sub C. And this is also the susceptance of the inductor, B sub L. And this is the condition for us to be in resonance when the susceptance of C, this one here, is the same as the susceptance here. And if that's true, then we are in resonance. Then we can still derive our f of r from here, or I can just give you f of r, because you can continue deriving this by simply substituting xc, xl. This is omega xc, this is omega 1 over omega xc, and this is omega xl. So let's write that 1 over omega c. Or before we do that, we can first distribute, cross multiply. So this is xc times rl squared plus xl squared is equal to xl times rc squared plus xc squared. And what is xc? This is 1 over 2 pi f. Our f now here will be the resonant frequency, which is what we want to solve, times rl squared plus xl is 2 pi f of r L. Then you square that, and this is equal to xl 2 pi f of r L multiplied by rc squared plus 1 over 2 pi f of r c and you need to square this. And next, we can cross multiply here and here. So RL squared plus 2 pi f of RL squared equals this one times this one. So we have 2 pi f of r, we square that. Then we multiply L and C. And this is equal to this. Then you can continue to do that, solve for f of r here by distributing this one here. Then after that, after distributing, then we can actually do that now. So 2 pi f of r squared times LC times r's of c squared. Distribute it here. We can cancel out 2 pi f r at the denominator, so we have plus 2 pi f r. Then we can also cancel out c, so we only have L here. Then still we have RL squared plus 2 pi f of RL squared. At this part, it should be 2 pi FR squared. Then we can move these two at the other side and solve for f of r. So I can just give you f of r. F of r now will be just equal to 1 over 2 pi the square root of LC multiplied by the square root of RL squared C minus L, then we have RC squared L minus L. And this will be our resonant frequency if you have this case here. So if you look at these two, they are different. But if we try to disregard or make RL and RC be small equal to 0, so if this is equal to 0, this is equal to 0, then this will become negative L over L, and negative L over L is just equal to 1. Square root of 1 is just 1, and we retain 1 over 2 pi the square root of LC, which is the formula for ideal inductor and capacitor. So these are the other cases for parallel resonance.